All right, can you hear me?
Yeah.
Okay, all right, so I'm going to get started. I guess it's just one of you today. So just stop me if you get confused anywhere. I'm going to talk about really the next two labs. The first lab I'm going to talk about is DC circuit analysis lab. And then I'm going to talk about the DC motor lab. So let me talk about this first one, and then, so this one's going to be due on November 5th, and the motor lab is going to be due on December 3rd. And the procedure for the DC circuit analysis lab is not too complicated. You're going to be building a more complicated circuit, the one we studied in lecture the other day. Okay, and we're going to analyze it in a lot of detail. And then this is really more like a project, and I'll talk about both of them. The DC motor lab I'm just introducing to you. I will say some more as we go through chapter 29. It would probably be not the upcoming Tuesday, but the following Tuesday, where I will have covered everything you need to know regarding the motor lab. Okay, let's start with this DC circuit analysis lab. This is lab 4. And this lab is based on the circuit I discussed in class. The circuit I talked about in class looks like this. R1, R2, I'll get out of the way. So we analyzed this circuit in class. And in this lab, what we're going to do is verify Kirchhoff's current rules. And granted, this first part of the lab, this circuit you can analyze using series and parallel. I understand that. But we're going to use it to verify Kirchhoff's current rule and the loop rule. So the first thing you want to do is you're given 4 resistors. The resistors you're going to be using are the ones listed right on here. You must use those resistors. Okay? And also you'll be taking a picture of your circuit and putting the picture of your circuit in your lab report. So you measure these 4 values, and then you're also going to measure the current from the power supply. So you will put an ammeter in series with this circuit, and you'll do it on a proto board, and you're going to measure I sub S. So I sub S is going to be this current, the current through the power supply. Okay, so you'll measure R1, R2, R3, R4, and I sub S. You'll also measure the power supply voltage. Then you'll need to measure the voltage drop across each one of these resistors. So you're going to be measuring the voltage across R1, the voltage across R2, the voltage across R3, and the voltage across R4. So you're measuring 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 items. Okay? All right. Then from that, we're going to calculate the current through each one of these resistors. Since you know the voltage through each one of the resistors, and you know the resistance value, then the current, for example, through resistor 1 is...
You froze for me. I don't see you moving anymore.
Okay. Yeah, I can hear my computer, the fan going. Okay, now I'm back. Thanks. So you'll measure the current, you'll calculate the current through this resistor by just using Ohm's law. The current through the second resistor, again, using Ohm's law. And you'll do the same thing for the third and fourth resistor. So those things you'll calculate. And we're going to use these values to verify the current rule. So you know that when the current reaches this point, it splits off this way and this way. This is I1 and this is I2. The sum of these two has to be equal to whatever you measured. And so what you're going to compare is the sum of these two to the measured value. The sum of these two is also called I sub s, so I have it right here. But of course, these currents, I3 and I4, when they reach this point, this junction, they combine again to also give you I sub s. And so again, you're going to try to verify Kirchhoff's current law by summing I3 and I4 and comparing it to what you measured. And you want to see if the measured value and the calculated values agree, which also means that you have to calculate the uncertainties in I1, I2, I3, I4, and I sub s. And I'll talk about how you get the uncertainties in these values. By the way, I noticed a mistake in the lab. Over the last few semesters, I've stopped having the students for the Ohm's Law lab, having them write down the uncertainty in their resistor values. So for the Ohm's Law lab, if you don't write down the uncertainty for the resistor values, that's fine, because I'm not talking about how to determine the uncertainty values until this week. And I'll show you how to determine uncertainties in a bit. Okay, so by making these 10 measurements, we're basically going to verify Kirchhoff's current law here and here. We're going to try to verify it twice. Now, I should say that when you're doing this experiment, at least part one, you have the freedom of keeping this ammeter in the circuit when you're measuring the voltages or removing it. If you remove it, you'll notice a difference between this I sub s and this I sub s because of the resistance of the ammeter. Okay, if you remove it. So it's up to you. And you should use the appropriate value, the appropriate scale, current scale. Okay, you don't want to use too big a current scale or too small a current scale, because you do want to get a lot of sig figs, but you might not want to get too many, because if you get too many, then the resistance here is large. And you should also start by, when you're measuring the current, if you want to figure out what is the best scale to use, you can always estimate the total current in your circuit. Or you can just put the ammeter on the highest scale and see what the value is, and then see if you can go to the next lowest scale. Questions on this?
No.
Okay. So the procedure is easy. What's hard about this lab is all the error propagation you have to do in this experiment. First of all, you got to use the manual to get the uncertainties of these values. Then you got to use error propagation to calculate the uncertainty of these four values. and these two values, which takes a little bit of work. And go back in the video describing this circuit. Although when I did the circuit in class, I used series parallel to completely solve it. Okay, so that's part one. Let me show you the circuit. I almost forgot. I wired the circuit for you folks, so you can take a look at it. This is the actual circuit. These two orange wires are for part two, because I'm going to hook up an ammeter between these 2 points for part two. Okay. For part one, you can leave them hanging or you can take them out. But this is the circuit. There's the power supply. Okay. I'm just going to connect the plug right here, and that's it. I can hold it horizontally so you can see that you can get a good picture of the circuit. Okay. Oh yeah, one more thing I forgot to mention. Somebody brought up this morning's class something about the resistance scale. I was confused about the resistance scale. So let me say something about that before I go on. On the resistance scale, you have a 200 ohm scale, a 2K ohm scale, a 20K ohm scale, etc. When you read the values on this scale, all the values from 0 to 200 ohms. The values of this scale are going to be 0 to 2,000 ohms. Actually, it's 2 kilo ohms. It reads everything in kilo ohms, and it's 0 to 20 kilo ohms. So these numbers are in kilo ohms. So what you see on the display is in kilo ohms. What you see on this display is in ohms. And then the other scales are either in kilo ohms or megohms. Okay, I just want to clarify that. There's one scale that's 20 megohms, so it would read between 0 and 20 million ohms, 20 megohms. Okay.
Wait, which scale reads in kilo ohms?
So all the ones that have a letter K in them,
Yeah.
that's kilo ohms.
Okay.
The ones that have an M in it are megohms.
Okay.
So the scale will be like the 2 megohm scale, the values will be 0 to 2 megohms. The unit will be in megohms.
Okay. All right.
So a 1,000 ohm resistor on the 2 megohm scale will read 0.001.
Okay, that makes sense.
Okay. All right. So part two has really 2 sections to it. There's 2 tables you have to fill out. Part one just has one table, table 1. Part 2 has 2 tables associated with it. And part 2, essentially the same circuit, except that you are going to place an ammeter between the label points A and C in the diagram. You're going to be measuring the current here. You're going to have this always there. This always has to be there.
That's for part 2?
Yes.
Okay.
So this always has to be there. This one, actually, for this ammeter, you're going to still measure I sub S. Once you've measured I sub S, you actually have to take it out of the circuit, because then you got to use that meter to measure all the voltages across all the resistors. Otherwise, you need 3 meters. We didn't give you 3 of them.
Okay.
Okay. So for this part, again, you already know what the R's values are, so I'm not going to repeat that. But the circuit has changed because you put this across. Ideally, the ammeter has no resistance, and so now these 2 points are at the same voltage. So you have a different circuit, and you'll measure the voltage across R1, the voltage across R2, the voltage across R3, the voltage across R4. You'll measure I sub S, and then you'll measure the current between these 2 points, IA sub C. Okay?
Okay.
Then you're going to calculate, again, I1, I2, I3, I4. You're going to calculate I sub S. Okay? You're going to calculate IA sub C. Now, IA sub C, let's think about it. You have current I1 here, current I3 here, and then this is the current IAC. And so this current is going to be I1 minus I3. And over here, this current is going to be I4 minus I2. And so you're going to verify Kirchhoff's law here by comparing the measured value for I sub s to the sum of these two currents. You're going to compare this measured value of IAC to I3 minus I1. And you're going to compare this measured value to I4 minus I2. And pay attention to the direction in which the current goes. So you have to actually hook things up right. You need to determine whether the current is going through the meter to the left or to the right, by knowing the polarity. So if you make
Yeah,
this...
because,
I'm sorry?
oh, just going with the current makes it positive and against it makes it negative, right?
Yes.
Okay. Like we did on Wednesday.
Yeah, if you put
Tuesday.
Go ahead.
Oh, no, that was all.
So if you put the positive terminal of the meter here and the negative terminal of the meter here, if you get a positive current, you know current's going that way. Okay?
Yeah. Mm-hmm.
If you get a negative value, then you know current's going that way.
Okay.
So you're going to determine that in the lab.
Yeah.
Okay. So really what you're doing is, in this lab, you're verifying Kirchhoff's laws. I haven't said anything about the voltage law. I'll get to that. Okay. But you're also learning how to analyze these circuits and make measurements and building them. And you'll find that once you've learned how to build a circuit, they say, oh, this is a simple circuit. But at the beginning, it's hard. I mean, I'm watching my students now. I'm watching our students now. They're in the lab here working on the experiment. And I'm seeing them, spending a bit of time building the simple circuit. But once they get used to it, once you guys all get used to it, you can say, oh, that was simple. And then you're going to move to this one. You can say, oh, that's hard. But once you start getting used to wiring things, then these circuits will look simple to you. At first, everything looks hard, but you'll get better at it. And all these circuits we're analyzing in this course are going to look simple to you. Okay. It just takes time. Okay.
Just curious.
Go ahead.
Do you wire do you do the electricity for your own house?
I'm sorry. Do I do my own? Do I do it? I don't. I have a friend who's an electrical engineer, and he's put in 2 of his own solar panel systems.
Wow.
The only problem is you have to do it to code.
Oh, okay.
So when you're doing wiring, you got to make sure you do it to code. And so I generally don't. I mean, I'll replace switches around the house. That's not a big deal, or plugs. That's not a big deal. But if I have to run new wires from the circuit box to somewhere else in the house, I need to get an electrician to do it, because then they'll do it to code.
Okay, that makes sense.
So the one thing I don't know are the codes.
Okay, that makes sense. Yeah.
Yeah, I can do it a lot. I mean, from the logic, I can figure out how to wire things, but following the rules is the local rules is different.
Yeah. I was just curious. Just you know the circuits and stuff, so.
Yeah, and it's really not. Your house wiring isn't too bad, except when you start going to like the fuse box.
Yeah.
Because you're dealing with high currents. I mean, I've even replaced the capacitor on my air conditioner. And that's actually dangerous. Okay, because the capacitor costs $20, but if you have them come over and fix it for you, it's like $400.
Yeah.
But that one I don't have to worry about any code. I just have to worry about not getting electrocuted. Okay. So we've talked about calculating IAC and I sub s for this part, but you're going to do this part twice. And I'm not going to have you do all the calculations the second time. And the reason why I want to have you do it twice is I want you to change the current setting on the meter. So the first time you do this, you want the meter on the highest current setting. So it has the lowest resistance. That'll be the 10 amp scale. And I try to choose the current value, the resistor value, so even on the 10 amp scale, you'll get a reading. If not, just go to the next highest. Okay.
So wait, sorry, on the first round,
use the highest scale that gives you a reading.
The highest scale, okay.
Yeah, the highest scale that gives you a reading, which should be the 10 amp scale. I chose the resistor values so that I think you should be able to use a 10 amp scale.
Okay.
You're going to get less sig figs on a 10 amp scale. Okay, as long as you get a non-zero value, use a 10 amp scale. Okay, if you have a zero value, then use the next highest scale. But you have the lowest resistance there.
Yeah.
Then the next time you do it, you choose a lower current scale. The lowest one you can use, actually. The lowest one you can use, because the resistance is going to be higher. You will get more sig figs, but then the resistance is going to be higher. And you're going to see this number change because of this resistance. You're going to see this number change because of the resistance in the mirror. And that's what I'm trying to show you, is the effect of the instrument on the circuit. So when you're making measurements, you also got to think about, how does my instrument affect the circuit? How does my instrument affect whatever I'm measuring? Because that's important in science. Okay. The only thing I'm not having you do in this lab is having you see the effect of the measuring voltage on the circuit. Okay. I just don't have time. We just don't have time. This will keep you plenty busy. So I'm not doing that. But I think if you take Engineering 17, he will have you do a lab where you get to see both the effect of the ammeter and the voltmeter on your circuit. Okay. Because that's important anytime you're making a measurement in science, is how does your instrumentation affect your results? How does it skew it? Are we okay with that?
Yeah.
So the next thing then is, I'm doing all these calculations. How am I going to figure out all the uncertainties? And I just found out that not everybody has the manual that came with the meter. So I'm going to have to photocopy it and email it to you guys, or put it on Canvas. Okay? So you need the manual for the meters, because the manual tells you the uncertainty in all the measurements.
So you can get the propagation of error?
Yeah.
Or error propagation, yeah.
So, and they're written in a way we're not used to. So I'm going to talk about that real quick. And I have a little paragraph at the end of the lab that discusses this, but I'm going to do it up here too. Suppose I have a multimeter. I'm measuring resistance. And my multimeter goes from 0 to 1,000 ohms. And I measured a value of 250.3 ohms. Okay? I go to my manual, and it says on this scale, because you'll notice it'll list the uncertainty on every scale. It's actually called the accuracy. Okay, because when they design this, the uncertainty takes into account random error plus systematic error. When we do our experiments, we only focus on random error. Okay, so it'll say accuracy. In my example, 1% plus 5 digits. And it's this term that's confusing. Okay? So let's say something like that, 1% and 5 digit, or 1% plus 5 digits, something like that. So what does this mean? So this last thing means is the uncertainty in the least significant figure. So if this is the measurement, the manual is telling me that my value, this last digit can vary by 5. So this can be 0.8. So my value can range between 249.8 and 250.8. So I have an uncertainty due to the fluctuation of that last digit by 5 values. Then I also have a 1% uncertainty. So I got to take this number, this measurement, and times 1%. And what am I going to get? I'm just going to write 2.5 for now. So I have a 0.5 ohm error because of this, and a 2.5 ohm error as a result of this. My total error is 3.0 ohms. Now, when I quote my error, my uncertainty, that reflects the doubtful digit in my measurement. The first doubtful digit is the 3. This next digit makes no sense. If this is doubtful, what does that mean? I guess it makes no sense. So this is telling me that my reported measurement should only be kept to the ones place. My measurement is, and I'm going to quote it 2 different ways. $250 plus or minus 3 ohms. Okay, so that's what this means. And so you're going to need to figure out what the uncertainty is based on the manual for these measured values. Actually, I mean, you can put this one, but we're not going to do any calculations with this one. Okay, you need to use the measure. So you need to remember what scale you were on when you made the measurements. So pay attention to what scale you were on.
So the uncertainty for the multimeter, that 1% plus 5 digits example, works for everything it measures, right? Not just resistance?
Well, it depends. I mean, you have to look at the manual. It might be a different value if you're measuring current. But
would it still be in the term of percentage plus digits?
Yeah. Oh, yeah. They're all going to be like that. They'll all be listed as a percentage plus digits.
All right, just making sure that wasn't unique to resistance or something. So.
No. It's just the format is the same for all of them. So in fact, in the lab, I give you one for current.
Okay. All right.
So you get a different one, but the formatting is the same.
Okay. By the way, you froze.
Okay. All right.
Thank you.
I'm hoping I get my new computers. Next month I'm supposed to get my new computer, so hopefully I don't have this issue. So we're going to have to do air propagation on all these calculations. And if you need help, just contact me, or you can always come by my office on Mondays and Fridays. So the one calculation, the uncertainty calculation, which looks the easiest, which most students have a hard time with, is this one. I sub S, anything involving a sum. I want to know the uncertainty in I sub S. And so I got to do my calculation with partial derivatives. Okay, so what's the derivative of this with respect to I1? Well, it's 1. What's the derivative of this function with respect to I2? It's also 1. And so this ends up being and I apologize for putting the I1 and I2 as subscripts. I didn't do that over there. Maybe I should change these, I guess. I keep making this mistake.
Oh, I wrote all mine as subscripts before, so you're
Okay,
good.
all right. I just don't want to, I should be consistent.
Yeah.
Okay.
You're good.
And whether this is a sum or a difference, the equation for calculating uncertainty is the same. There's always going to be a plus here. And then, of course, you got to apply the same rule for calculating the uncertainty in this guy. And if you look at table 1, 2, and 3, when you put the values in, you also got to put the uncertainties in. So really, this is the first lab where I'm having you do a lot of uncertainty analysis.
Yeah.
The Ohm's law lab, even though it says to list the uncertainty of the resistors, I'm not going to worry about it because I didn't discuss this at that lab. It just didn't. Normally, I don't have time to discuss it because I spend a lot of time talking about the diode and the curve fits. There's no curve fits for this lab, by the way. Okay.
That's just Ohm's law, right?
Yeah, just Ohm's law. You're making your graphs and curve fits.
Okay.
And of course, there's several questions you got to answer for part 1 and part 2. But one of the questions asks, does this value agree with this value? But again, you have to realize that this is a range of values, right? There's an uncertainty based on the uncertainty of the multimeter, and then here it's the uncertainty based on these two calculated values. And so if the range of values overlap, then they agree with each other. And then you can say, oh, my results verify Kirchhoff's current rule. Okay.
Okay.
Another question that's listed there is that it says verify the voltage rule. Okay. So you have to pick a loop in that circuit and sum the voltage drops. Do you get 0? Okay. But when you do that summation, not only must you do that summation, but you should also calculate the uncertainty in the summation, which basically involves a sum of squares of uncertainties. Okay, so you might get, excuse me, you might get, this sum will give you maybe 0.3 plus or minus 0.1. If you get that for your results, doesn't agree with the voltage law. But if you get this, that agrees with the voltage law. And this might bother you because the uncertainty is bigger than the sum. And that can happen when you're summing voltage drops, because some are positive and some are negative. Measuring 0 is very difficult. When I was a grad student, grad student and beyond, I learned how difficult it is to measure 0. It's actually tough to measure 0.
Yeah.
Okay. And so it's a small number, but then you have a collection of uncertainties associated with it, and this number can be significant when you're measuring something close to 0.
Yeah.
Okay. So when it says calculate the uncertainties in that question, do it. People tend to lose points in the lab by not calculating that uncertainty. Okay. All right. Yeah, just be careful answering the questions. There are quite a few questions on this lab. Part 1 has, let's see, 3 questions. Part 2 has 6. And they all tie to how well you know the results of your experiment and how well you can analyze the circuit. So let me talk about the next lab, the other lab, the motor lab. I'm just going to introduce it to you. And I know we haven't covered magnetic fields or anything like that, but I kind of want to get you to a point where you start thinking about it and doing it. It is due December 3rd. Don't wait until December 2nd to build your motor, because you have to try to make it work under certain parameters, okay? And you might get stuck. So let's look at the DC motor. I see it as more of a project. And when we're on ground, students have a blast with this lab, because they look over each other's shoulder and they try to build a motor that's better than the other student. Okay, they try to say, they compete. At what voltage did your motor work? And they try to get the lowest voltage. They try to make it operate the lowest voltage possible. So in your lab kit, you have this bag. This is your motor kit. You have magnet wire. The most expensive part of the kit is this magnet wire, which be careful with it, okay?
I thought it was copper wire originally.
It is copper, but it's made for making magnets.
Oh, okay.
It's not magnetic, right? It's copper wire. When you run current through it, then it becomes a magnet. Actually, so you have to put something magnetic, wrap something magnetic around it, like nails. So this has nails in it, tape, sandpaper, and the batteries, although you probably already use the batteries.
Yep.
Okay, and you're going to build, this is an old one. This was built by one of our Physics 110 students, but they worked under different parameters. This is what they built. This had a Halloween theme to it. Okay, and so they built this motor. It has really 3 important parts. Let me write the words down. It has an armature, a commutator, and brushes. So a motor is a device that converts electrical energy into mechanical energy. So basically, the idea is to run electricity through this device and get this thing to spin. And you connect this to the outside world, and whatever's in the outside world, you get it to rotate. Okay?
All right.
So the thing that spins is called the armature. This is what transfers the energy to the outside world. What I mean by outside world is outside of the system.
Yeah.
Okay. And then, so this is the armature, and then if you can see here, these 2 wires.
I like the Frankenstein, by the way.
You like the Frankenstein?
Yeah.
They're called the brushes. And
The
then
wires that wrap around inside, or right there.
The stiff wires that let's see if I can. These stiff wires.
Are they right next?
Yeah.
Oh, okay, yeah.
Those are the brushes, and then this thing that's messed up is called a commutator. I'll show you a better one. So let's see if I can. This is a better commutator.
Oh, those nails right there.
The copper strip.
Yeah.
That's the commutator.
Okay.
And this is where the transfer of energy occurs from the from the power supply to the armature.
Okay.
Okay, so these wires are the brushes in this particular one. It's basically
Okay.
the commutator brushes make the electrical connections. So, I mean, the instructions that are given have you build this thing without the Frankenstein and the
Yeah.
yeah. So this U-shaped piece with the wire wrapped around it, this forms an electromagnet, and you need
Okay.
the nails to be magnetic. Okay. Some people use other material. I'm going to show you one that's a little bit different. So this was included in the kit. The students bent the nails, wrapped the wire like so. This is electromagnet, and then this is part of the armature. You also have to wrap wire around the nails. Okay.
Oh yeah. Okay.
Okay. And again, you want these materials to be magnetic. This piece doesn't have to be magnetic, but it's a nice thick nail. It's a good support. So mainly this guy has to be magnetic, and this has to be magnetic. These other support nails don't have to be. Okay.
All right.
All right. Make sure you wrap the wire nicely around. Like, I don't know if you can see the bottom here. This one's well wrapped. Okay.
Yeah.
You have to be very good in wrapping the wire. Some students are not. And the motor doesn't work as well. Here's one from a student that designed the motor, but the armature is not wrapped very nicely. I don't know if you can see that. It's hard to do this in front of the camera. It's not wrapped very nicely, although this is a nice piece for the electromagnet. And the student wrapped it very nicely. The problem is this thing moves around back and forth.
Yeah.
And these brushes are kind of loose. I mean, they're really loose. And so this one ran at 5 volts. So you don't have to build exactly what's prescribed, but if you look at the document, it tells you what the rules are. Okay, you have to hook up everything in series, not parallel, and you have to your armature has to be a certain diameter. Okay, the minimum diameter is given. The problem with this one too is that the armature was too heavy. And the moment of inertia, because of the wire wrapping around the armature, it wasn't a nice. The mass wasn't distributed uniformly. That makes your moment of inertia higher. Okay. So how am I going to grade this? There's 2 parts to grading it. It's graded on the questions on the last page. That's 10 points. And graded on the operation of motor. That's 30 points for a total of 40. So if you can get the motor to run on those 2 D-cell batteries, you get the full 30 points. Okay, and then the answers to the question, usually people do well on this. They usually get 8 of 10 or 10 of 10 on this part. Okay. So if you do this part and you turn in the questions, you generally get like 38 out of 40 points or 40 out of 40.
Okay.
Okay. So the hard thing is making it work at 3 volts. You can make it work, but making it work at 3 volts is the challenge. Now, when the lab is on campus, you have to make it run on 2 volts. So you guys are a little bit lucky because we're online. Part of it is the fact that you don't have the equipment, the same equipment that we do to test it.
Oh, okay.
So the lab says to make a video showing, in the video you want to show the motor, show your face. Okay, you want to show the motor, you want to show your face. Your name has to be on the motor. I can see your name on the motor, and I need to see the wiring on the motor, and I need to see the power supplies that run the motor so I can evaluate what voltage it runs at. Okay, so you can do that. However, you can always come here, because we have much better testing equipment than you probably have at home, and you can troubleshoot the motor here, And then also test it. You don't. If you test it in person, you don't have to make a video.
Okay.
All right. If you come to me and say I want to test my motor, it doesn't have to be me. It could be Tyler. We'll sign off on the document, and it'll probably sign off also on the motor itself, saying what voltage it ran at. Okay.
Okay.
And then you'll give the sheet that's signed. You'll give it to Tyler, and then Tyler will give it to me. So I think doing it in person is a benefit to you because you have better testing equipment here. If you're doing this at home and you need more than 2 D-cell batteries, you got to go buy more batteries.
Yeah.
Don't use the 9-volt batteries because the internal resistance is higher. And I am not sure, I won't guarantee that the power supply that comes with your Ohm's Law lab will work for you because of the fact that it's current limited. It might or it might not work. I'm not sure. The higher the voltage, the less likely it'll work. Okay.
Okay.
Any questions on this?
Not currently, partially because it's not what I'm working on right now. But yeah.
So I'll discuss this more. I'll discuss this lab more when we do magnetism, which we'll probably start on Tuesday, and then
next week.
Yeah, and then the following Tuesday I will probably finish the whole chapter, and that's when you'll have enough information on the operating principles of the motor, just the basics.
Okay.
All right. All right. So that's all I have to say.
And our test is a week from today, right?
Yes. Your exam is next Friday.
Okay.
And this is the last meeting in which I record a lab lecture this semester.
Today?
Yeah, today's the last one where I record a lab lecture. Everything else is in person from now on. In the lab, not the lecture.
Yeah.
Not the Tuesday
Not
meeting.
the Tuesday.
Yeah. Okay, so you folks have a great weekend.
You as well. Thank you.
Thanks.
All right. You're welcome.